All right, so we have our test coming up on Wednesday, and that's in here from 1 to 150. Now, if you're a distance ed student and you can't make that time, that's no problem at all. Just contact me and we'll make some other arrangements. So, if you're a distance ed student, that's no problem. Just let me know and we'll figure something out. Now there's also a quiz that I'll have available. I sent out that Moodle message with a link to the Red Cedar Hall 111 Testing Center where it will be at. I'll also offer it here on Friday too of next week. So if you want to do it then you can, but if you don't, you don't need to. We will have a little bit of class after the quiz, so we'll start up class about 1:30 to go over a few things, but I'll record that too, all right? So that's what we got coming up. Well, I gave you out that review. It's available on Moodle. There's 2 pages of old test problems, and then there's a list of things. We'll go over that in a bit of detail on Monday. It'll be the plan. Okay. So have a look at that over the weekend. All right. So we good with all that? We got any questions on anything? Everybody has a copy of that review, right? Okay. Good deal. All right. Well, off we go. We're going to start covering some new stuff. This will not be on the exam, so keep that in mind. Well, the other thing I'll mention is that Moore's Circle will only be on the quiz. I won't put any of that on the midterm, okay? So Moore's Circle is just on the quiz. Yeah, it's just too much to get into an hour. I can't get all that in there. And it's probably helpful to just focus on Moore's Circle for that quiz, I think, okay? All right. And now what I call the quiz is actually part of the midterm. I mean, that score will go into your midterm. I don't know how many points it'll be, 14 or 15 or 16 or something like that. I'm not sure, but that will go into your midterm score. Okay. So let's kind of keep going into another bit of biaxial stuff here. We were talking about in uniaxial, if you're just pulling on something, that E, that modulus elasticity, is the relationship that allows you to relate stress to strain and strain to stress. Now that is the case for unidirectional loading, if you're just pulling in one direction or pushing in one direction. If you have a biaxial load, it gets just a little bit more complicated, okay? So I'm on page 410. And what we've got here is just some sketches that show what would happen if you have a block and you pull on it up there in the upper left-hand corner. Not only will it get longer in the direction you pull, there will also be lateral effects where it will get thinner on the sides. That's the meaning of lateral, right on the side. Now, if you push on a block, as I'm showing over here, you'll get the reverse happening. It'll get shorter in the primary axis you're pushing in, which in this is the x-axis, but it also bulge out on the side. Okay, and that'll be the lateral strain that causes that. So when we look at the relationship between stress and strain and for biaxial loading, we have to consider both effects, the primary axis, but also the lateral side as well, okay? So the basic relationships that we use here is that E is sigma over epsilon. So the axial strain is the stress sigma over E, the modulus. But we also have to consider the lateral strain, which is negative nu times whatever the axial strain is, okay? So when we do biaxial strain, we got to consider both of those is the idea. All right. So if we're looking in the x direction for the strain, and again, I'm on page 410. What you would do is you would take the main stress in the x direction, sigma x, and just divide that by E. And that's just this relationship right here. But you also have to then consider the the stress in the y direction, because that's lateral to the x, all right? So what you would do would be to take minus sigma y over E, but then you multiply that by nu. That makes it, that accounts for the fact that the y direction is lateral to the x. Okay. Then you can pull out a term of 1 over E and factor that out, and what you get then is the strain in the x direction, epsilon x is 1 over E sigma x minus nu sigma y. So the nu is in there again because y is lateral to x. It's not the primary cause of epsilon x, but it does affect it because it's lateral. Okay. So we all right with that? It's called Hooke's law, was the term for this. All right. You can do the same thing with epsilon y, same idea. Epsilon y is 1 over e sigma y because that's the primary stress minus nu sigma x, the lateral stress. Now, if you're loading from 2 dimensions, you also get strain in the z direction. Both sigma x and y are lateral, so that'd be minus nu over e sigma x plus sigma y. Okay. So that's the 3 strains you can find: epsilon x, epsilon y, and epsilon z. So what you can do here, if you know what the stresses are and you know the material properties, you can figure out how much deformation you would expect for a biaxial condition. You can also back solve those for the stress based on the strain. You could plug in the strain in the x and y directions there, and from that figure out what the stress is. And that's commonly done because sometimes they use strain gauges, and they'll read things and get an input from a strain gauge, and from that figure out what the stress is. And again, you'd have to know the material properties, nu and e, to do that. All right. So that's the basic relationships there. That's called Hooke's law. Okay. Now the shear strain is the same thing we've been doing all along. There aren't any really fancy sideways or lateral type effects from different types of shears. So gamma, the shear strain, is just tau x. So gamma xy would just be tau xy over g. Gamma xy would be, gamma yx would be tau yx over g. All right. So that's really all you do for the strain. It's just that basic modulus relationship. You could solve it either for the strain, so if you know the stress, you can predict what the strain will be, or you can solve it for the stress. So if you measure the shear strain, you can multiply that by the shear modulus to get the stress. Okay, now the one thing on this is that if you have a positive, is the sign convention for strain. So if you have a positive tau xy, which would be upward on this vertical face, the reference face, on that vertical plane, if that's upward and you get that typical strain pattern for that being positive, so the shear strains would do that. Boy, I've got that going the wrong direction there. That lower one ought to go to the left. I don't know if it does on your copy or not. It should. I've got a typo there on my old copy. Do I have that going to the left on the bottom? Or yeah. I do. Okay, I fixed it. It looks like okay, good. All right. Now, if you have that stress pattern, what that's going to do, if you look at that, if you think of these stresses as being vectors, which actually, they're not really, but they kind of act that way, the net pull would be upright and down left. So those 2 opposite corners would pull out. The other 2 corners would come in, okay, to be pushed in. Okay. So you'd see an effect kind of like that on the corners. So what that means is that lower left-hand angle for positive shear stress will get smaller, okay? So for positive shear stress and positive shear strain, the lower left-hand corner angle gets smaller. Y'all seeing that okay? How those corners will pull out? Okay. And then if you got negative shear stress and negative shear strain, that lower left-hand angle gets bigger, okay? So you have to remember to kind of flip your normal relationships there. Positive shear strain makes the lower left-hand angle smaller. Negative shear strain makes the lower left-hand angle bigger. Okay. Now, I drew this one smaller just because I ran out of room on the page. That's the only reason. There's no other reason for that. Okay, so just in case you were wondering about that. It's doing pretty good when I was working down the page. It looks like I could have planned ahead a little bit better, but anyway, there you go. Okay, so there you go. So now what we can do is let's kind of go through a little chain of events here and look at this block that's 3 centimeters by 2 centimeters and 4 millimeters thick. That's on the next page, 432. And let's apply some stress to that thing, and let's see what the final shape of it will be. Because as you could infer from what we just went over, it's not going to be a rectangle anymore. Nor is it going to be 3 centimeters by 2 centimeters anymore. It's going to change shape when we apply stress to it. And that's true of any material, and it just depends on the modulus. Okay. Looks like I have some trouble with my shears there too. That one from A to B ought to be downward. Is that fixed now? I hope. Okay, good. All right. Okay, so what we're going to do, we're going to find the final dimensions of this thing after we apply those stresses. Now, I've got a little note here. This is usually how I find final length, so I don't end up doing too many calculations. I know that the delta, the change in length, is epsilon times L0, whatever L0 is. Well, L final then is the original length plus delta. That will be the final length. So L final will be L0 plus epsilon L0. So a quick way to get to a final length is just to take your original length times 1 plus whatever the strain is. So usually I use this little relationship because it's quicker than finding delta independently than adding it to the original length. This does it all in one step. So I'll typically just apply that to get a final length. Okay. All right. Good. So off we go. So the first thing to do is to find sigma x, sigma y, and tau xy. So we just fill those in, and then we just start running these formulas. It's not really, maybe the most exciting thing you're going to do in your life here. You just plug that stuff in and run the numbers. The challenge on this will be to kind of figure out what this thing will look like after these stresses are applied. So, this is that biaxial stuff. So we just find sigma x, sigma y, and tau xy. Just remember to get the sign right on tau xy. So the shear on that vertical face is up. That would rotate that thing counterclockwise, so that's positive 15. Okay. So negative 30 megapascals. A megapascal is 10 to the 6 newtons per meter squared, plus 20 and plus 15. Okay. And then once we got that, we just start plugging everything in. I give you the formulas. It's just a matter of plugging the stuff in. Okay. So the modulus, we got all the moduli, that's the plural, and they're up here. Okay. We got these values, so we just plug the stuff in. All right, so epsilon x is 1 over e sigma x minus nu sigma y. So that's going to be 1 over 400 times 10 to the 6th newtons per meter squared times the quantity negative 30 times 10 to the 6th. That's the sigma x. Minus nu 0.25 times sigma y, 20 times 10 to the 6th. And when you run that, you're going to get negative 0.0875. That's the strain in the x direction. So the way I think about that is that means the thing in the x direction is going to get shorter by about 8.75%. That's how I look at that number. Okay, and the way I got that was I took 1 over e times the primary thing that causes it to get shorter, which is sigma x, but then I have that lateral effect of sigma y, so I go minus nu times sigma y. Okay. So what I'll do is I'll say, okay, if that thing is going to get 8.75% shorter, that means the final length is what, 91.25% of the original. The way I get that 91.25 is I'm going 1 minus the strain. Okay? So basically what I'm doing there is taking 100% for the full length minus the 8.75%. But of course, strains we don't express as percent. We want decimals for them. So that's kind of what's going on, okay? So I'm just taking 3 centimeters times the percentage for the ratio of the final length.
That's the deformation.
I'm sorry now?
That's the deformation.
Yeah, that's actually the final length. So that kind of rolls the deformation into the original length, kind of combines them together. All right. All right, so we can just go ahead and do that on all 3 sides, okay? And just use epsilon x, epsilon y, and epsilon z, the formulas for that. Just run the numbers, and you'll come up with the strain and then the length. So epsilon y applies to the length AB. So 1 over 400 times 10 to the 6 times the quantity of 20 times 10 to the 6, which is sigma y, minus nu 0.25 times sigma x, which is negative 30 times 10 to the 6. So that ends up getting plus 0.06875. So in the y direction, it gets 6.875% longer. So the final length will be 2 centimeters times 1 plus 0.06875, 2.14 centimeters. All right. Okay, then we got epsilon z. Both stresses are lateral to epsilon z, so it's minus nu over e sigma x plus sigma y. You know, just remember your signs and all that. So we get negative 0.25 over 400 times 10 to the 6 times negative 30 times 10 to the 6 plus 20 times 10 to the minus, I'm sorry, 20 times 10 to the 6. And what we get out of that then is 0.00625. So it's going to get longer, deeper, I don't know what the word is, that LAE will get a little bit longer, 0.625% longer. So that'll just get a little extra lengthening there, 4.025 millimeters. All right. So that's basically how we're going to predict these deformed lengths here, okay? You got any questions on that? All right, and then we have an angular change too, because we have that shear on there. If all we had were these tensions and compressions, they would just still keep in a rectangular shape, but we got shears on there too. That'll change the angle, so this thing will turn into a parallelogram. Okay, so we just take tau over g, and we got those numbers, 15 times 10 to the 6 newtons per meter squared for tau, the shear stress, that's positive there. And then g is 160 times 10 to the 6, so that comes out to be 0.09375 radians. So that's 9.375% change in the angle. Now it's also a radian measure. You could think about strain as being either one. So I think about it as being a radian measure. So that original angle was 90 degrees, that's pi over 2 radians. So it's going to change by 0.09375 radians. Now it's a positive shear, so that means the angle gets smaller. So you got to remember to switch the sign there. So you subtract that radian measure off. And when you convert that to degrees, you get 84.6 degrees. You got any questions on that? Yeah.
And it's pi over 2 is
90 degrees is pi over 2 radians. So the answer you get out of this formula is in radians. So I just take pi over 2 minus that radian measure and then convert it back into degrees. Yeah, it started off as a rectangle. So it started off at a 90-degree angle. Good? Okay. So that's ABC, okay? In the lower left-hand corner, the right-hand corner will just be the same strain, but the opposite sign. So the angle will get bigger by that amount, so you end up at 95.4 degrees. So that thing's changing shape by 5.4 degrees. ABC gets smaller by that amount, BCD gets longer by that amount. Now, I will mention that I used some really low moduli on this just so we could plot it up and see what it looks like. I mean, in reality, you're not going to get, steel is not going to deform this much. That just wouldn't happen, okay? But I just do it so we can draw it up and look at it, okay? So we're good with that? So why don't we plot this thing up? It's on the next page. So there's the original to scale shape, 3 centimeters by 2 centimeters. Okay, and let's see what's going to happen. The new length for BC will be 2.74 centimeters. The new length for AB will be 2.14 centimeters. I just pulled those off of the previous page. I'm just on the next page, 433. The new length for AE, E's back behind here, that'll be 4.025 millimeters. Okay. Now, gamma is 0.09375. Now, you can look at this in different ways to plot up what will happen to angle ABC and BCD. But angle ABC should come out to be 84.6 degrees, and angle BCD should come out to be 95.4 degrees. Okay? So that's the information that we would start with to get the final shape of this thing plotted up. Now what I have there, I have a to-scale plot, pretty much, at least in the X and Y directions. I've got 10 small squares per centimeter there. That's my scale. So if you look at where these marks are, they're every 10th small square. So that means each small square is what? 0.1 centimeters. That's the idea, which would be a millimeter. Okay. All right. Now, to get those angles, there's another way to do it, okay? So I've got 84.6 degrees and 95.4 degrees, but there, when you're plotting, there's a little fancier way to do it maybe. What I'm going to assume is that half the shear strain occurs on either one of the lines, because what's going to happen here is if you kind of take a B as a reference point, which we will do, what's going to cause the change in that angle ABC is the deformation of this line. That angle's getting, what's it doing? It's getting smaller. So I'm sorry, I'm going the wrong way. The deformation of this line and the deformation of that line. Both lines are going to rotate a little bit, and the net result is that final angle will be less than 90. So instead of trying to plot up that angle, the 84.6, what I'm going to do is I'm going to take this shear strain to be in radians, and I'm going to assume that half of the shear strain occurs on each of the two lines. So the total change in angle of ABC is 0.09375. I'm going to take half of that and rotate each line by that angle. That's how I'll represent that shear strain. Now that may not be exactly what's happening in reality, but it should be pretty close. Okay?
That angle between the red line and the original line should be half of that.
Yeah, right. This should be, this angle here should be 0.0469 radians, and that angle there I'm going to make 0.0469 radians.
How do we, I'm assuming you're going to show us next, but how do we account for the other deformations, like putting that corner B?
Yeah, yeah, they're all going to move around, and we're going to just take them one at a time. We're not going to get too fancy about it. We're just going to look at the X deformation, the Y deformation, then we're going to look at this angular deformation. And we're going to, what's that?
We're going to do it all separately.
Yeah, and we're just going to add the results together. We're going to have to declare kind of a reference point, and I'm going to make that B. So I'm going to say B doesn't move, and I'm going to do everything from there. Okay. Now to get those rotations, I'm going to realize that for a small angle, the radian angle is about equal to the tangent, which is opposite over adjacent. Okay, and if we can even test that out, for example, for that, just to prove this to you that I'm not just talking here, let's look at 5 degrees. Okay, 5 degrees, and that's a pretty big deformation really in reality. If I convert that into radians, let's see how many radians that is. So 5 times 5 divide 180. It's 0.0873 radians. I just want to show you that this relationship works pretty well. That for small angles in radians, that the radian measure is pretty darn close to the tangent. So if I take the tangent of 5 degrees, what do I get? .0875 degrees, 0.0875, okay? So 5 is a pretty big angle, and it works pretty darn well for that, okay? And keep in mind also, we're engineers, okay? I'm not too concerned about 0.0002 degrees difference. That's not much, okay? All right, so we're going to use this approximation here that a radian measure of a small angle is pretty much equal to the tan. The tangent is opposite over adjacent. So if I want to know how much the opposite side will move, which is what I want, the deltas are right there and there. That's the opposite side. We'll take the radians, which is the tangent, so they're essentially equal, times the adjacent side. So I'll take that half gamma, which is my radian measure, times 3 centimeters, and I'll get 0.141 centimeters. And then I'll take my half gamma, which is my radian measure, times 2 centimeters, and I'll get 0.0938 centimeters. So what that's going to equate to is this squiggly green line here. That's the deltas that I'm going to have on either side on account of that angular deformation that's caused by the shear strain. Okay.
So that 0.141 centimeters, is that side of A?
That is what's going to happen. That's how far C will move.
Oh, okay.
Because I'm holding B as kind of my reference, and I got a 3 centimeter line for the 0.141. 3 centimeters, so that's that line there.
Okay, so then that's the deformation on C.
Of C. Well, I'll do it here next. Okay. All right. We're good? All right, well, here we go. So let's see what we got. We don't have much going on here, do we? Okay, let's do it this way then. Okay, so we've got those numbers. Now let's plot these deformations. Let's start with C. Now what's going to happen to BC is it's now going to be 2.74 centimeters long, okay? It's not 3 centimeters long anymore. We calculated it on the previous page. It's 2.74. Well, that means it's right about there, is about where it's at. It's gotten shorter. Each one of these small boxes is 1/10 of a centimeter. So just the normal or axial deformation puts it right about there. But it's not going to stay there. See, that's part of the story. That's this bit. But it's also going to rotate a little bit. It's going to kick up by 0.141 centimeters. So that point is going to end up right there. Okay. It's now 2.74 long. It's its new length. It's not 3 anymore, but it's also going to have a little bit of kick out on account of that shear, and that's 0.141 centimeters. Okay. Now, AB is going to get 2.14 centimeters long, so that's going to put that right up there. But it's also going to kick in a little bit, 0.0938 centimeters, which is just a little bit less than 1/10 of a centimeter. So it's going to end up there. So there's A prime, and there's B prime. The assumption here is that I'm holding point B constant. So the final shape of this thing, and I can have a hard time drawing a straight line on this screen, of course, but it's going to look something like this. I'm going to connect those dots, then I'm going to draw parallels. So I'll draw a parallel line here that is parallel to I call that B prime, that's C prime there, I'm sorry, that's a C prime. So I'm going to go from C to the new D parallel to AB, or at least I'm going to try. It's not going to be easy, but I'll do the best I can with that. And then I'll draw another parallel here, parallel to BC. I'll kind of head up that direction, like so. Okay? So what I'm plotting up here is where these new points are going to end up. I have to declare a reference point, which is somewhat arbitrary. You know, I say this point doesn't move, I'm going to measure everything from here. And so I'm getting the final shape of that rectangle. Now it's going to get a little bit thicker too into the page, but not much. So I won't, you know, it's going to be tough for me to include that in here too. But that's actually going to be 4.025. So just a slight change into the page. So instead of being a rectangle now, that bar or whatever it is will start looking like that plate. So that's the idea. Okay. I had a student who was working an internship who was taking this class, and he told me that where he was working, they had one of those conveyors that are made out of like cylinders on axles, so you just kind of roll it across. And they were pushing some stuff that was really heavy, and what it was doing, it was deforming those cylinders, and they were starting to whack into each other as they rolled, okay? Because they were flattening out as that big heavy weight came over them, and they started to the technical term for that is interfere with each other. They started hitting, which the informal term is they were smacking into each other and making a bunch of noise, and the conveyor wasn't working too good. That's the conveyor, that's the informal way of saying that. And so they did an analysis like this to kind of see, okay, we got these stresses, it's going to cause these strains, what's going on here, and what are we going to do about it? Okay? So that's an example of why you might be interested in this, okay? Especially in the mechanical world, because if you start building machines where one moving part interacts with another moving part, you know, that's when things get a little interesting there. You know, if you've taken apart an internal combustion engine, there's rings around the piston that have to seal right on the cylinder walls, and they're flexible, right? Because there's all these heat changes going on in there, and there's all that stuff, so there's got to be a little bit of slack in there, but there's also that need to get a perfect seal so that you get good compression and all that. So that's one solution to that. Okay. So we're good with that? Okay. So there's a little better sketch, but that's the idea, okay? So we declare a reference point. The common place is to have a reference point, usually on a square kind of object. I'll put it in the lower left-hand corner and draw my deformations from there. In a round object, I'll put the reference point in the middle and show the deformations going out from the middle. It's somewhat arbitrary what you call the reference point. Maybe it is, maybe it isn't. I mean, here, obviously, if you've got axles rolling down through the center of those rollers, that would be your reference point. You would assume they wouldn't deform too much. And you'd calculate your deformations from there. Okay. All right, so that didn't come out too well, but that's just an attempt to show that came out pretty close to the angle, which was 84.6. And you know, that scan obviously didn't work too well with my protractor, but there's 90, I can see that, and there's 80. So that's, you know, it's not a bad approximation on 84. It's somewhere in the middle between those two. It's not bad. It's hard to tell exactly on there, but it's in the ballpark, okay? And keep in mind, these are kind of these exact mathematical models, you know. They're as good as we're going to get, and we go with it, you know. But you always want to throw a little safety in there, you know. I was just listening to one of the people here that teaches in our water treatment program, and he was talking about that. You know, we do this math, and we get it in the ballpark, but, you know, when you actually start running a water plant, well, you know, maybe you're getting this removal, maybe you're getting that. It's a little variable. You know, the numbers don't give the perfect story, but they give you a shot at what's going on, and, you know, an operator will kind of take them and go from there, you know. Like, you know, always keep that in mind with some of these numbers we run. You know, they're good, but they don't always perfectly describe the situation. All right. So we good with that? All right. Okay. Now, that's a little bit there on what's called Hooke's law. Now we got another little thing to do here for biaxial. We're going to jump ahead a little bit. Got a nice simple little set of relationships here. Thanks. Okay, this is biaxial strain, okay, which again relates to what we were just doing. This is a little, I think the word for this is gnarly, I think, this stuff. So this is on page 470. it's kind of these involved equations. I had to kind of set them sideways on your page there to fit them in there. This is a kind of, it's like biaxial stress, but it's for strain. It's the same idea. So let's kind of look at the forest before we get too deep into the trees here. The idea on this is just like with biaxial stress. If you know what the strain is going to be, because these are for strain, in the x and y directions, you can predict what the strain will be at any angle you're interested in. That's the big picture on this, okay? And this is the derivation on those equations. Again, these are somewhat simplified, but they'll get us the best number we can get, okay? So, and I would never test you on a derivation like this, so don't ever worry about that. What we'll focus on is how to use this stuff, but I do feel obligated to at least go through this because this stuff doesn't come out of the sky. Someone works it out and figures it out, okay? So that's what we're up to here. So what we got there is a rectangular little element, one of those little calculus elements. So it's got dimensions of dx and dy. Okay, what we're going to do is strain it in 3 different directions. We're going to strain that rectangle. And based on that, we're going to look at what the change in length is of a diagonal going across this thing at the x1, in the x1 direction. We're going to call that diagonal ds. So if we start taking this corner and straining it in different directions, deforming it, we're going to see what the effects are on ds. We're going to do that 3 times, and then we're going to add up the totals and get the total deformation for each one of these things we're doing. That's the idea. Okay? So the first thing we're going to do is stretch this thing out in the x direction. So we're going to give it an epsilon x, strain. The deformation, that'll be epsilon x times whatever the original length was in the x direction, and that's dx. So that deformation there is epsilon x dx. So what we got then is a right triangle right there, or pretty close, and that thing's going to stretch out like I'm showing there. The top hypotenuse will be epsilon x dx, and what we're going to be interested in is the lengthening right here, the delta right there. Now the angle of the vertex of that triangle is going to be pretty close to this angle that we're measuring across our rectangle for ds. Not exactly, but close enough, okay? So what we're going to call this distance here, this lengthening that I'm calling out right there, is epsilon x dx, which is our delta in the x direction, times cosine of that angle. Okay. And I'm going to call that delta d prime. I think that's what I called it anyway. Is that what I called it? Yes. I'm going to do that 2 more times. And then we're going to add these 3 effects up. So that first one's for epsilon x. I'm going to do it again for epsilon y. So that delta there will be epsilon y dy. I'm going to get another right triangle. This hypotenuse here will be epsilon y dy. I'll have these 2 legs and pretty close to the angle theta right there. So this will be epsilon y dy sine theta. That'll be delta d prime prime. So I got 2 delta d's now, delta d prime and delta d prime prime. And that was so much fun, I'm going to do it one more time because I've got the shear strain right here. If I apply that shear strain and change that angle, I'm going to get a delta up top there that's gamma xy now times dy. The shear strain times dy. That should be equivalent right there. Pull out my little triangle. There's the hypotenuse, which is the gamma xy dy. There's my angle theta right there. Hard to see, but there it is. So that's going to be this little delta that I want will be gamma xy dy times the cosine of theta, because I'm adjacent to that angle theta. That's my delta d. I'm going to call it prime prime prime. So I got 3 of those things, and I'm going to add them up to get the total effect of doing all 3 things at once. So I looked at each little event as one single thing, then I'm going to add the 3 effects together. And I'm going to get that expression there, a little bit cumbersome, but that's what we end up with. So there's our delta D total. Good with that?
Where did your hypotenuse come from on the x?
On which one?
Gamma x, y, dy?
Okay, what's happening here is I'm applying a shear strain right there in that lower left-hand corner. That's going to cause an angular change, and that's going to rotate that line. So I'm going to end up with a little delta here as that thing kicks over, a little delta right there. That's going to cause the same delta right here, and then I'm going to extend this dash line, and between that delta in green on the top and that dashed line extension right there, that's where that triangle is coming from. Now, it's not perfect, but it's, you know, it's in the ballpark is what we're doing. Okay. And we're going to add all this stuff up and get a delta D total. Now that's a delta. What I want is a strain, so I'm going to divide it by the original length of ds. So I'm going to get dx ds, and what that is cosine of the angle theta, that original angle. There's ds, ds. So dx over ds is cosine theta. Okay. Dy ds is sine theta, and I've got one other dx ds for cosine theta. I'm going to plug that into the formula. I'm going to throw some trig identities at it. I think those are half angle formulas. I can't quite remember, but I've got the trig identities there. Plug those in. Collect terms. There we go. That's what I want right there. Okay. So what that tells me is the strain at some angle, I'll call that epsilon x1, is epsilon x plus epsilon 2 over 2 plus epsilon x minus epsilon y over 2 cosine 2 theta times gamma xy over 2 sine 2 theta. Okay? So that what I'm going to do here, if I know the strain, normal strain in the x direction, epsilon x, and normal strain in the y direction, epsilon y, and I know the original gamma xy, shear strain in the xy direction, and I know an angle that I'm interested in, I can calculate the strain, the normal strain at that angle using that formula. Okay? And that's really what I want you to know. If you know epsilon x, epsilon y, and gamma xy, and know what those things are, you can plug them into that formula and find the strain that would occur at any angle you want. That's equation 71. I'll also point out that it looks an awful lot like formula 25. So it's 71 on the back of your formula sheet. It's very similar to the stress biaxial equation, 25, with the one exception is we got a 2 under the shear here. That's the only difference. Okay. That was fun, wasn't it? Let's do that again for shear. Okay, now the shear gets even a little bit more complicated, so I'm not gonna, I'll go over it, but I don't want to spend a year at it. I mean, frankly, it's not worth it. I do like to have a look at them and get some idea where they come from. So it's kind of important, but it's the same technique here. What we're going to do is look at the shear strain on that ds. Now that's going to be a little bit of an angular change on that hypotenuse. So if I start stretching this thing out horizontally, I'm going to get a little bit of change right there where that line will rotate just a bit. And I'm going to add up all of those angular changes and from that infer what the shear strain is at that angle theta. So I'm going to get a lengthening there again of epsilon x dx. Got my angle theta. I want to know this little change right there, and that's going to be epsilon dx sine theta right there. Okay. And then I'm going to look at how much that rotates this original ds line in red. So that's going to move down by epsilon dx sine theta. The original length of it is ds. Okay, so that angular change will be the inverse sine of epsilon x dx sine theta divided by ds. That's going to be an inverse sine. Okay, so I'm calling that alpha prime. That's telling me how that hypotenuse rotates on account of that shear strain that epsilon x strain that I apply. I'll do the same thing in the y direction, and I'll come out with that little triangle right there. I'm interested in this side right here, which is going to be epsilon y dy cosine theta because it's adjacent to the angle theta. I divide that by the original length and take an arc sine. For a small angle like this, the arc sine and the angle itself in radians are pretty much equivalent. So my alpha prime prime is epsilon y dy cosine theta over ds. Okay. One more time here, I'm going to look at the shear strain. That's going to kick this thing over by, I'm going to end up at this little triangle right there. I'm going to pull that thing out. I got gamma xy dy just like I had previously. I got my angle theta. That's going to be the change right there in green. Gamma xy dy sine theta. Okay. So once again, I'm going to get an angular change on that original hypotenuse ds. Arc sine gamma xy dy sine theta over ds. I don't need to worry about the arc sine part because it's not significant for these small angles. So what I get is gamma xy dy sine theta over ds. To get that total angular change of the hypotenuse, which is what I want because that relates to my shear strain, I'm going to add those three things together. I'm going to realize that dx over ds is cosine theta, dy over ds is sine theta, and I'm going to collect terms and get what I call an angle alpha there. There's the formula. So alpha, that angular change in the hypotenuse, is minus epsilon x minus epsilon y sine theta cosine theta minus gamma y sine squared theta. Okay? And that is formula 77. That tells me how this central hypotenuse line will rotate when I start applying strains of epsilon x, epsilon y, and gamma xy. Now that's the rotation of a line. The shear strain that I would want would be the rotation of two lines, just as we were doing in that previous example there with the rectangle where we rotated two lines to get the shear strain. It's the same thing here. To get the shear strain, I would take alpha and add it to the angle beta there. Add those together. That'll get me the shear strain for that original angle right here in red. Okay? It's the rotation of two lines. So I get the rotation of a line, which I call alpha. The shear strain is the change in an angle. I'll call that gamma. Now the formula for beta is the same formula as we have for alpha, except we've got to put theta plus 90 degrees in more every time we see theta. What we're doing there is we're changing from this angle, and now we're going to add 90 to it and get over to that other side. That's what's going on. So instead of theta, we're plugging in theta plus 90. Cosine theta plus 90 is sine. Sine theta plus 90 is the negative of cosine. Plug that into the alpha equation. We do have to do a little change in sign because we get a little different rotation on that line, but what we end up with is the beta equation right here. Add alpha and beta together, we get the shear strain. And I had to kind of put that down in the lower right-hand corner. We had to do a little bit of trig substitution, and that's what we end up with for our gamma equation, okay? And I'm sorry, I just don't want to bog down too much in that. I know I'm kind of running through that a bit. But the bottom line here on this stuff is shown on page 490. Okay? So epsilon x1, which is the strain in the x1 direction, is found by this formula right here. That formula is formula 71. Very similar to the biaxial stress equation. The shear strain at a given angle is shown by this formula. Again, very similar to the biaxial stress equation for shear. That's equation 72. That tells you how an original angle would change once you apply strains in the x and y directions. Okay. There is a third equation that we use for this stuff that is alpha. That tells not how an angle would change, but how a line would rotate. There's alpha right there. And that is equation 77. Like that. Okay. And basically we develop those equations for those derivations that I just showed you, which are based on looking one at a time at the effects of applying strains in the x and y directions on an original rectangle and what would happen with that diagonal when you do it. And we're just looking at the geometry and trigonometry of that. All right. Now, a couple of little things I'll mention here. We're going to reference an angle theta. Now, this time it's measured from the horizontal. I'll explain that a little bit later, but instead of the reference plane being the vertical this time, it's horizontal. So there's our angle theta right there this time for strain. Gamma xy is measured in radians. Okay. Alpha and beta are the rotations of a line. Gamma is x1, y1 is the rotation of two lines, which gets you the change in an angle. Okay. We'll go through an example of this, but that's on page 490. That's really the stuff that you really want to know. Okay. We'll go through how to apply this stuff on Monday a bit. Our goal is going to be to figure out strains at given angles and shapes of objects after we apply load to them. That's going to be our goal. Let me get you one of these things to do here. We'll make this due Friday because you got that test coming up on Wednesday. How about doing 221 and then sketch it up on 221B? So 221 and 221B. And these will be due on Friday of next week. Now, these are both written up for you, so that's page 14A and 14B. Okay. Good to go?